Okay, so we have finished the limit comparison test. Okay, so you have at least two methods in conversion test. You can directly compare with some series that you know that easy to be concluded, easy to have the results. You can compare, or you can have the limit comparison test using the ratio between AN and BN. And when they resulted in a positive constant that is greater than 0, which means the conclusions will be the series will be both convergent or both divergent. It depends on what kind of series is it. If this is convergent, then this is also convergent. If this is divergent, this is also divergent. Okay. I think this is pretty much easy to be applied. Okay? When you have a function that maybe you can take some comparison, and then you can just take a limit and then take the ratio. Okay? When you have the positive, then you can definitely answer the questions. Okay? But when the result is 0 or maybe negative, then maybe you need to change the method. Okay? Change the method. Okay, so you have at least the method. First is divergence test. But let me just review a little bit. So divergence test, and then integral test. The divergence test is the easiest one. So when you have the limit of the sequence that is not 0 or doesn't exist, definitely the series will be divergent. Okay? It's the final conclusion. And then the integral test. Integral test. So this is limit of n, maybe this, or it doesn't exist. Integral test, the functions need to be continuous, positive, and always decreasing from 1 to infinity. Whenever you find this, then you can go to integral test. And if you can compute the improper integral, then it will be converged. And then you have the comparison test. You have direct comparison and then limit comparison test, which we are just discussed. Now the next one, if this is 11.5, this will be about the alternating series. So alternating series means that the series, it has alternate signs of changing. So the signs will be changed. So maybe positive, negative, or negative, positive, negative. Okay. So as example, maybe you have 1 and you know the alternate signs by looking at the formula, -1. Or maybe another example, we start from the negative. And this is what it looks like. Okay? But maybe we just look at the example first. Okay? So at least from these two, we can identify the alternate series from this -1, right? From this formula here. So either we have the AN will be either -1
n minus 1. And then the rest will be, let me just write as Bn, okay? It can be any sequence. Or we can have -1 with power of n and Bn. You can also have n plus 1 also. Okay, well, it depends. Okay. And Bn should be in a positive number. So Bn is a positive number. Okay, and this is the visualizations. But let me write some terms, maybe right here. Okay, if the alternating series okay, let's say we have this -1 with power of n minus 1 Bn. This is B1 minus B2 plus B3 minus B4 plus B5 minus ... This, let me just write it like this, okay?
If I have this alternating series, if I want this series to be converged, what can we do about this B1, B2, B3, B4, B5?
Remember, okay? If you look on this
1 minus half plus 1 over 3 minus 1 over 4.
This is not really.
Okay, if we have just 1 over n, if we add 1 over n, and we know from improper integral, if you remember, that will be divergent. That will be divergent. 1 over n harmonic series, if you plus, it will be divergent. Last week we discussed that. But then, if we have alternating signs, maybe you can imagine and count. Maybe 1 minus half is a half, plus 1 over 3, and minus 1 over 4, plus 1 over 5. Maybe you will reach some numbers, right? Can you imagine that? Okay. So when you have this number is going to be smaller. Okay. The after terms, okay, the second term is smaller than the first term. This is smaller than the previous terms. I mean, just looking at the number. Okay. If you just cover your signs. Okay.
And also, if we look on here, okay, if we imagine,
B1 is greater than B2, B2 is greater than B3, okay.
And then if we look on how the graph visualize,
so start from 0. So plus B1. So here, this is our partial sum, S1. And then the second term, minus B2. Stop here. This is our partial sum of 2, the second term. And then plus by B3. And minus. And eventually, you will end up probably around here. Okay? Using limit, we have simplification here, maybe. That's our S. Right? Okay. So, we can make out that the alternate series to be convergent.
that is if satisfy that the Bn plus 1 is less equal Bn, which means
the next term should be smaller than the previous one. Okay?
And then you can make sure that it's converged. And also, the limit itself of Pn is going to be 0. Okay. So this will conclude the series is convergent. So these two. So whenever you find the alternate series like this, first thing, looks up the Bn, check the limit, and then check how's the terms. Okay. If it satisfies these two conditions, we can just say directly the series is convergent by alternating series. You can write it by alternating series, or you can just write convergent and state these two statements, and that's okay. That's fine. Right? Now we are looking at the harmonic series with alternate signs. Okay. Okay. If we're looking on this 1 over n, we take the limit. It's 0, right? It's 0. And when we check the terms, that is always going to be smaller. The bn plus 1 is going to be smaller, smaller, smaller. We say that this will be converged by alternating series. Because the limit and or we can say 1 over n plus 1 is going to be always smaller than 1 over n. Now, for this 1 over n, the harmonic series, which is it is diverged if we exclude the sign, it's diverged. But when it's having the alternate sign, it's become convergent. So we have the conditions where the original series is diverged, but when it has the alternate sign, it's become convergent. We can say this convergence is conditionally convergent. We can say that this is conditionally convergent. So at least there are two types. When you have the series itself, if it is converged and the alternate series converged, we call absolutely convergent. But when it's diverged, but the whole thing is converged, we can say it's conditionally convergent. It's just to make sure how the series will be. Okay, how the series will be. I will go back later to take more details. But let me take to the estimate sum, okay, before we go through the conditionally convergent and absolutely convergent. So let me go through the alternating series estimation. Okay, if S is the sum of n minus 1 Bn, where Bn is positive, and this is and S is the sum of alternating series that satisfy first is this, and second, this is just similar what we did. Satisfy this. We have the Rn, the remainder that we set up in the integral test. The remainder will be different. The difference between S and Sn, and it should be less equal Bn plus 1. And we can set the Rn to be S minus Sn less than Sn plus 1 minus Sn. Okay. This is just saying that the actual S that we are looking for is in between Sn plus 1 and Sn. Okay. It's on between those two. Okay. So what does this means? Okay, it means that for several terms that you want to know the error. For example, you want to know the first 8 terms. The first 8 terms. So n is 8, n is 8. Meaning the error, the accuracy is always less equal than the Bn plus 1, 8 plus 1, B9. So B9, the terms B9, if you check maybe 1 over n plus something, that will be the accuracy, the error that is on the range of this. Okay. So this will be the represent your error. Okay. So the Bn plus 1 will represent your error. Okay, I think it's clear from here. Okay. Okay, now we talk about the absolute convergence and conditional convergence. Let me write first is the definition. Okay, so series is called absolutely convergent if the series of absolute value is convergent. Okay, so it's clear. So the original one is convergent. It has the alternating series that's also convergent. So the absolute values converge. Now the other series is called Conditional Conversion. If it is convergent but not absolute convergent, but let me just write if the series converge, but the absolute value, the series of absolute value, is diverge. So it's called conditional conversion if the series converge, but the absolute value diverge. And if it is absolutely convergent, then the series, of course, will be converged. Okay. Let me add more notes here. Then to make sure that this is the conclusions. Okay, now let's define or determine the series I think the first one is simple enough. We take the absolute value, we get 1 over n cubed. It's already converged. We can say it's absolutely convergent. We can take this. And we can say that this is P series where P is greater than 1. Then we can say this is converges, and in particular, this will be absolutely convergent. Okay. And how to know this? You need to write absolutely convergent, conditional convergent. It depends on the questions. Sometimes the questions, they specify if this is conditionally convergent or absolutely convergent. But in general, in all the methods that we are using, the conclusion just converge, diverge. That's the final result. Okay. This is just a conditions, the conditions for some convergent series, for some convergent series. And I think this one also easy to follow. This is still the P series, okay? Just also reminding you to the improper integral that we did, that this is p less, or if you want to include 1 also, okay, that this will be a divergence. Diverges. But if you look on the series, okay, if you look on the series, maybe we're writing with green, okay, if you look on the series, okay, if you check bn plus 1 is smaller than bn, okay, if you check, we can check with the this is true, right? And then the limit also 0. The limit of the, maybe I will write 1 over. So since this is true, then we can say the alternating series is converges. Then the conclusion, since the absolute value diverge, but the series is converged, we can say that this is conditionally convergent. Okay, I hope you don't get confused on my writing here. So first check the absolute value, and then check with alternating series theorem. Then you can check the n plus 1 and n. You check the comparison between these two. And then check the limit of the bn. And if that's 0 and the next term is smaller than the previous term, then we can say that the alternating series becomes convergent. And since this is divergent convergent, we are finally saying that it's conditionally convergent. Okay, one more, I think, because I given you these two, maybe one more to conclude. Okay, what we can do from this series. Does the limit 0? No, right? So we can say limit is not 0, which means that the series diverge. The series diverge by divergence test. Later, I will put some practice and exercise. I hope at least you try 1 or 2 each part. My idea or my goal for you is, at least for some specific series, you will know how to do or how to use the tools, okay? Which method you are going to use, okay? And then you will learn some patterns from the series, okay? So, because there will be a typical series that they will always like that. They will always behave like that. Okay, that is the alternating series. It's actually not too complicated. Okay? You just need two requirements for the satisfaction. First, the limit of the Bn equals 0. Second, the series need to be getting smaller. The value need to be getting smaller, and then we can get its converged. And there are typically 2 kinds of convergent: conditional and absolute. Just that. Okay, so I hope it's pretty much simple enough. The next one is ratio and root test. So this is 11.6. Maybe I will write some method. Okay, the description. What is this? So first is the ratio. I believe the ratio is one of the also the most applicable method. Okay, one of the most applicable method. So ratio test is you're just using your series, and then you compare or take the ratio with the n plus 1. Okay? And there will be a three equations. If you have the number is less than 1, you can say it's absolutely convergent. If you get greater than 1 or getting infinity, then you can say it's divergent. But if you get 1, then the test will be no conclusion. Okay? So you need to use another way, another method. This is also most applicable test, okay, for the series. Okay. Because most of the series, it can be solved by ratio test. Okay, so how do we get the reasons behind the number, yeah, or the criteria? Maybe we can set up, so set the number that is probably from L, or maybe we set up R, okay, this is between L and 1. Okay. And if we have the limit, if we have this is equal L and L is less than R, the ratio will eventually be less than R. And then exists an integer capital N, so that the ratio of these two will be less than R whenever you increase the integer, whenever the integer is getting increasing. Or we can look this set up as an plus 1 is always less than an and R. You can think R in terms of the ratio in geometric series. So this is related or having some correlation with the geometric series. So the ratio, the common ratio. And if we take the n, okay, if we take the n, let me write here. If we take the n, and an n plus 1, and an n plus 2, we can obtain, that is, if we change the small n with the integer, the capital N, we can take this. First is this, okay? And second, we have we can set up this if you would like, you can expand more. Okay. Maybe I will write in a new page to be clear. Let me copy this here. And if you have a and plus 3, we can set up this to be n plus 2 n plus 1 r cube. And in general, you can say that we have n plus 1 is less than an with r with power of k. This is for k is greater equal 1. Now the series itself, if you take the sum, the series will become convergent because of the geometric series. The sum of geo series, where r is between 0 and 1. Okay. And similarly, if you have the ratio greater than 1, it will be not equal 0. The limit is not equal 0. And therefore, it's diverged. Okay. Okay, let's take a short break. Okay, now this is just a simple proving, and I think we just go to practice some example on how to apply. Okay. First is probably having the series of So the question is just to see whether this is convergence, divergence, okay, or maybe if it is any conclusion from here, okay. Well, in a shortcut, okay, this factorial here, usually it is obvious that you are using ratio test. Okay? So whenever you test the convergence and you see any factorial, most of the time the ratio test will be work. So let's try ratio test. Okay? So check with ratio test. So let's say this is our an. So an plus 1 is n plus 1, n plus 1, and maybe this is n plus 1 factorial. So limit, well, we can start from the limit. And take absolute value. And then we can exchange the n plus 1 and plus 1. And I will directly write this is n factorial divided by n with power of. let's take some time to solve this. This factorials I will add n plus 1, okay? So I will write this maybe using blue colors. So n plus 1, n plus 1, and n, okay? And this will be n plus 1, and then n factorials. Then n factorials, and n with power of n. Now we have canceled this. Now we have limit this cancels also. So we will have n plus 1 over n and with power of n. Anyone still remember what is this? This is the definition of E. Okay. Definition of E. Okay. This is E, definition of E. And since E is greater than 1, so the series is diverged by ratio test. I think aside from ratio test, we can also look on, because this n with power of n and n factorials, we can see that this is actually n multiplied with n multiplied with n, right? N time. And the factorials start 2, 3, 4, 5 until n. And it's always, right? You can imagine that it's always greater than the n, okay? And or you can set the an doesn't approach 0. So the series will be diverged. This is actually the divergence test, okay? But with some explanations, okay? With some explanation on this ratio. Okay? And in some cases, the ratio test will be failed. In some cases, it will be failed. For instance, the easy one, let's just go back to the harmonic series. Okay? If we think we are going to have using the an plus 1 over an. Okay. This will be resulted in 1 over n plus 1 and 1 over n, or n plus 1. Okay. If we take the limit, this is resulting 1, right? And which means it's inconclusive. So you need to try another method. And of course, this is, we know that this diverges, right? The harmonic series. Or if we have the p test, the p series, 1 over n squared. Similarly, we can take this ratio test and take the conclusions to be n over n plus 1 and then squared, which is also equal 1, okay, if we take the limit. And this is also inconclusive. So that's the ratio test. Okay. So just using the limit, and then take comparison between an plus 1 and an. Okay. But this is example for inconclusive. Okay. So this is where ratio test is failing. Okay. Now there's another one. Okay, so ratio test, and the second one is root test. Okay, both have the same or similar conclusions. L less than 1, L greater 1, and L equal 1. Okay. Okay, let me write some words. So root test is not really used much, but you will see the pattern obviously. So first is if limit of the an absolute value, and okay, and this is equal L. Maybe I will write so that you don't really need to write a lot of things. Let me just write L. First is L less than 1. Okay. Then the series is absolutely convergent. L greater 1, or limit is infinity. Then the series is divergent, and L equal 1, okay, same root test, is inconclusive. Since it has the square root of the power n, then it must be obvious that the series will have some power of n. Okay? So whenever you see a series, for example, the series, it has the power of n. So for obvious reasons, you will use the root test. Okay? So it's not really widely applicable to all the series. For those that only have the power of n that we can apply, okay? Most of the time. So whenever you see any series which has the set of power of n, then you can apply this one. And the result is the same as the ratio test. Depends on whether the L is equal 1, less than 1, or greater than 1. Whenever you find less than 1, you can write it's absolutely convergent or convergent. Okay. But when you have L equal 1, then you need to use another method. So like for example, this one, we can just take the square of n, and then we can simply remove the n. Okay. Then simply we can set this. Okay. Or maybe let me just write as an. Okay, so we have now 2n plus 3 and 3n plus 2. And then by using the limit concept, then it turns out to be 2 over 3, which is less than 1. So the series, as a conclusion, the series is absolutely convergent by root test. So this is, I think, the last typical methods for determining whether the series is converged or not. After this, I will go some review. Okay, some review. And after review, maybe going to have some introductions on the next section. And to help you more practice on how we solve chapter 11, maybe next Thursday I will go to some review on maybe practice. Maybe we can have several questions. Okay, I think root test is I think pretty much obvious. Okay. Now let me just go to some strategy. Okay, strategy. So first, the one that is easiest way, the one that is practical to use is the divergence test. So check the limit of the sequence, and whenever you find not zero or doesn't exist, then you can stop and then conclude that it's diverged. The second, if you can see any p series, this is converge, this is diverge, this is diverge. And third, if you can see any geometric series. So this is more like priority. Okay? But it also depends on your preference. Okay? Usually this is for 3 cases that easiest way to use. Okay? It's 3. And for comparison tests, you can check with direct or limit comparison. And another one that is still applicable is alternating series. Of course, if it has the -1 with power of n, then it should be alternating series. And 6 is ratio test. 7 is root test. And 8 is the integral test. It's not really that useful, so I will put at the end. Okay. So if you cannot use the divergence test, maybe you see the series, what this looks like. Can we compare to another series? Can we compare directly? Can we use limit comparison? And if it has this -1 here, it should be alternating series, and I think you can check using the alternating series. And I think it's not that complex. And you have ratio, root test, and integral test. But some of the series, I think most of them, you can go check the ratio test because I think it's practical, and you can see the result. Okay. But when it's just equal 1, then you need to check with another one. Okay. So ratio test, maybe you can go put here, maybe here. Well, it depends on you actually. Okay, I will go review the strategy maybe next Thursday. I will just give you some intro to next section, 11.8, which is the power series. I believe the series will be useful if you are learning in in more about practical engineering, because in a sense you will need in the future courses. Okay. Now let's go to some introductions. Okay. I will just go later Thursday to discuss this strategy. Let me just go slightly power series. Okay, 11.8. Okay. So the series that we have learned so far, okay, we learn about the series that has these. Okay, so we have a sequence, and then we have a sum, we have a series, right? So what is power series? Okay, so power series is a form that includes variable x. So we can write the form like a sum, and then c n x n. And c is just a constant. And sometimes we can write in more general, so sum so this is a general form of power series. So C, this is a variable x. This is a constant C. Okay, if you notice that it resembles the polynomials, right? It resembles the polynomials. If we take the Cn to be equal 1, okay, so all the C inside will be 1, we are getting that if we start from 0 of x with power of n, this will resulting 1 plus x squared plus x cubed plus plus x with power of n plus . And we know that this is actually similar to the geo series, right? So we have the ratio r in between here, right? And we know that the r, if we set the r in between, so r is actually x, right? And the x will be having a convergent if it's between -1 to 1. So it will be converge. And if x greater 1 is diverge. We can write also the power series in more general way that includes the x minus a. This is called power series in x minus a. or power series centered at A. Now, because of this x minus a, later when we learn about the convergences, we learn that the ratio here, we can imagine like a circle, like a circle. It has some radius. It has some radius. So the convergence will be in between of some part of x, okay? Some part of x, and maybe that will be for a later part discussion. But for now, let's just look here, okay? That if we want to check the sum of the geoseries, if we take this as a geoseries, we can take this and say that this will be equal with 1 over 1 minus x, right? The sum of the geoseries. This is A, this is R, right? So eventually, you get a function. So it's from series, you can represent a function. That will be the later part also. So the power series is quite helpful for learning in more advanced engineering, okay? Learning more about the usage of the series and how it's represent a functions. Okay? So it's quite wide. The application is quite wide. I think I will stop here and I will go deliver your results, and you can have some time to check your quiz. Okay? So I will stop here.